Alright, so in this lecture, I'm going to be focusing on few-shot learning for named entity recognition for this task in natural language processing. And we use decomposed meta-learning for that. So I'm going to be focusing on this paper in 2022 from Microsoft. Few-shot name entity recognition systems aim to recognizing novel class name entities based on only a few labeled examples. In this paper, we present a decomposed meta-learning approach which addresses the problem of few-shot name entity recognition by sequentially tackling few-shot span detection and few-shot entity typing using meta-learning. Of course, I have a playlist for NER, which I've explained some of few-shot learning methods in there. So here we take the few-shot span detection as a sequence labeling problem and train the span detector by introducing this mammal. I've explained mammal in this playlist, so I don't repeat it. For few-shot entity typing, we propose mammal protonets, mammal-enhanced prototypical networks to find a good embedding space that can better distinguish text span representations from different entity classes. So again, like any other few-shot learning, we have support and query. Support is S, query is Q. And we have train and evaluation. And so we assume there is no intersection for training and the novel labels. And so we have S, the support is S and the query is Q. And we want to find the name entities. The name entities could be just one word or could be a span or even a nested span. So this is a framework of proposed approach. First, it is decomposed in two modules. A, which is entity span detection. We detect the span. And then entity typing with parameters gamma. And the two models are trained. There are many ways to train these models. But they are trained independently. The span detection model aims at locating all the name entities in an input sequence. The model should be type agnostic. For example, we do not differentiate the specific entity classes. For basic detector, we implement a strong span detector via sequence labeling. So we apply this begin, intermediate, order, end tagging scheme instead of standard BIO2 scheme because we want to provide more specific and fine-grained boundary information. So given an input sequence with L tokens, we first leverage an encoder to obtain contextualized representations for all tokens. Then we get this H, which is the representation, and we give it to a linear layer and then softmax to get the probabilities of each of begin, intermediate, out, and end, and etc. So the learning loss with respect to X is just the average cross entropy of the predicted label distribution and the ground truths over all tokens. So we train a mention detection model by repeatedly simulating the meta-testing phase. So we first randomly sample an episode. Each episode has support, has query, and training data from train and perform this inner update. We then evaluate that theta prime on the query set and perform meta updates. And because we are doing meta learning as well, so this is how we update over many tasks. For meta testing, we first fine-tune the meta train span detection model. So for entity typing, we aim to assign a specific entity class for each span. In the previous module, we were just finding the boundary, but now here we know the boundary, so we just want to see the class of that. For example, which entity it is, which type of entity it is. So entity typing, ProtoNet is very easy because you just take the average of all samples per class K, for example. It's very easy, and you know how to represent the span. From I to J, you just one way or there are several ways to represent the span. One of them is just simply just summing all of the, for example, from I to J, we have representation HI plus 1 until Hj. We sum all of them, and this is a good representation for a span from I to J. Once we get the span, we compare this span to all of our prototypes to see which one, because we have many different prototypes. So, for example, if it is here, then it has closer, so we get that this one belongs to this entity type because we have different entity types. For example, here we have 3 different entity types, so we have 3 different proto centers, and you know how to calculate the cross entropy loss. And we get, for inference, we get the highest probability very easily. So we elaborate on the procedure to integrate the ProtoNet, the classical ProtoNet that I explained, and the model agnostic meta learning. So for meta update, we first recompute prototypes. This recomputing we should do. Of course, there are other ways to do that. And they use PyTorch 1.9 instead of PyTorch 2. We leverage 2 separate BERT models, and we train all models for 1,000 steps. And their dropout probability is fair. It's just 0.2. It's not too big, not too small. And 1% warm-up. So this is a case study for span detection. For example, we say this is a span, this is the boundary. And after that, the second module, which is to understand exactly which one is. So span train a span detector in the fully supervised manner. But how does MAML enhance the ProtoNet? Why do you want to augment them? We first compare the proposed MAML proto to the conventional ProtoNet. Because the MAML, if you augment it with proto, you will see that it has some benefits. Of course, it is not in my slides, but in the original paper, you will see the TSNE visualization of that.